So just like we did with the substitution reactions, we're going to have two types of eliminations based on kinetics. So two different mechanisms based on the kinetics of that mechanism. So two types of elimination reactions. And again, this is based on kinetics. Right? Basically two different types of mechanisms. So our first one is going to be an elimination bimolecular or E2. So just like our SN2, this one is second order. The rate law is going to involve both the alkyl halide and my base. Instead of nucleophile, we're going to say base in this one, but it's essentially my electron-rich group, right? It's going to take place in a single step. So it is second order. My rate law is rate equals alkyl halide, and then for this one you can still put nucleophile if you want there. Sometimes I do. Sometimes I'll use base just to differentiate between the E2 and the SN2 mechanism, or rate laws we should say. So second order, it is going to take place in a single step, so it's concerted. Right, both the alkyl halide and the base are involved in that step. Because it only takes place in one step, that step is my rate determining step. Right, if I only have one step, that one step has to be rate determining. If we were to compare that to our E1 mechanism, so elimination unimolecular, this one is going to be first order, right? That's what the 1 in E1 stands for. And the rate law for my E1 reaction is actually the exact same rate law as my SN1 reaction. So only the alkyl halide is involved in that rate determining step. So it's going to be a two-step mechanism. The first step is the rate determining step, RDS. Only the alkyl halide is involved in the rate determining step. And it is good to know that this is the same rate law, and it's actually going to be the same first step as an SN1 reaction. Often we're going to, if something's going to go SN1, it's also going to go E1. The step, same step is, the first step is the same for both of them. So they actually compete with each other. Often we'll get both the substituted and the eliminated product if something is going to go SN1 or E1. So let's look at the E2 mechanism first. E2. So remember, this is the one where both my alkyl halide and my base is involved in that step. So this one is concerted. Right? All the bonds that are being formed and broken are happening at the same time. Because that's happening at the same time, it does have a specific geometry. Just like our SN2 reactions, right, had to follow backside attack because the leaving group was leaving at the same time that my nucleophile was attacking, that had to happen from opposite sides. Because all of this is happening at the same time again, it does have a specific geometry. So the base in the leaving group must be anti to each other, and they have to be on the same plane. So if one's going up, the other has to be going down. If one is going out, then the other has to be going back. So the base and the leaving group must be anti to each other. And then if they're anti to each other, they are going to be on the same plane. So this second part is kind of redundant, but and on the same plane. So two different terms for this. Our book uses anti-coplanar. So anti and then coplanar, they're on the same plane. And then sometimes it's actually called anti-periplanar. That's how I learned it. So I say it that way a lot. Which means around the same plane. They both are anti, they're both on the same plane, just two different words. So we would say an SN2 mechanism is backside, right? Backside attack. Here, our E2 is anti-coplanar or anti-periplanar. Again, two words for the same thing. The important part is that the base and the nucleophile are anti to each other and then on the same plane. So let's go through an example, and I'm gonna draw some stereochemistry out on this, so just kind of bear with me as I get it drawn. So I'm gonna have my bromine and the hydrogen that we're eliminating both in the plane of my iPad here, and then we'll have this group coming out at us. And then I'll have another hydrogen here that's going back behind. And then we'll have a hydrogen on this one coming out, and then that methyl group going back. So essentially I have 2-bromobutane, and the butane is kind of in the plane of coming in and out, and then the hydrogen and the halogen that I'm going to eliminate are up and down. The reason I'm doing that is I want to make sure that I show the proper geometry of that elimination. The hydrogen that we're going to take and the bromine that's going to leave, remember those need to be anti to each other and on the same plane. So they're on the plane of my iPad. I have the hydrogen going up, I have the bromine going down, so they're opposite. If I wanted to, just for fun, and I'll erase this after, but let's say I wanted that hydrogen to be the one that goes away, then I would have to have the bromine here where this hydrogen is, right? They're now coming in and out. Because the hydrogen's going out, the bromine needs to be going back. So that would be anti to each other, but still on the same plane, so still anti-coplanar that way. So just make sure that the hydrogen are eliminating and the halogen are anti and on the same plane when we do this. So let's get a base in here. So we'll use hydroxide. It's 3 lone pairs. So again, this one's concerted. All the bonds that we're forming and breaking are happening at the same time. So the hydrogen is going to be taken by those electrons on my hydroxide ion. So the lone pair on hydroxide is grabbing onto that proton. At the same time, the electrons between the proton and the carbon are going down to form our new pi bond. And then the carbon that the bromine is attached to would have too many electrons, so my leaving group is going to leave. And again, all of this is happening at the same time. So the hydroxide ion is grabbing onto the proton. The electrons that the proton were bonded to that carbon with are going down to form the new pi bond, and my leaving group leaves. So just like we did with the SN2 mechanism, with the E2 mechanism, we are going to show that transition state. So with our concerted reactions, right, the ones that take place in one step, I do want you to draw the transition state for me. And we do need to pay attention to the stereochemistry of that. So remember, in all of our transition states, we're going to show a dotted line for all the bonds that we're forming and breaking. So those 2 carbons I just drew are the carbons where I'm forming that new pi bond between. So the bond to that hydrogen is being broken, so it's dotted. We're forming a bond between that hydrogen and the hydroxide ion, so dotted. I'm forming a new pi bond, dotted, And then that leaving group is leaving, so we're breaking that bond, so dotted. And again, that hydrogen-carbon dotted line needs to be anti to the carbon-bromine dotted line, and then also on the same plane. So I have one going up, the other going down. If one was coming out, then the other would have to be going back. I'm going to get my other groups on here. And then our notation for a transition state. So those brackets. And then our double dagger symbol, and then our product. Is my new alkene. I also have water and then bromine floating around. You don't need to show me the water and the bromine. I really only am focused on the organic product, but if you wanted to show it all, there it is. So an example for our E2 mechanism, sorry, E1, we just did E2. So remember, this is the one that takes place in 2 steps, meaning our rate determining step only involves the concentration of one of our species, in this case, the alkyl halide. This was also the same rate law we had said is an SN1 reaction. So this was first order. Only the alkyl halide is involved in the rate determining step. So this one is going to take place in 2 reactions, in 2 reaction steps. We are going to go through an intermediate. So in our first one, I'm going to draw a tertiary alkyl halide. Let's actually use a real example. Let's put a bromine there. And what's going to happen is my leaving group is going to leave. So same first step that we would see with SN1. So leaving group leaves. And then we're going to go through that carbocation intermediate. In chapter 7, we said if you go through an intermediate, do watch out for rearrangements. So since I'm going through that carbocation, rearrangements are possible. So look for carbocation rearrangements. Remember, we're only going to have a rearrangement if we can make that carbocation more stable. In this case, it's already tertiary. If I did some sort of a rearrangement with it, it would either end up primary or secondary, which makes it worse. So I'm not going to have one in this case, but do watch out for that. It is possible to have resonance also. If I had an allelic or a benzylic carbocation intermediate, I would have some resonance. So watch out for rearrangements. We should say end resonance or resonance. We'll give that 2 exclamation marks also. Also, do note this is the same first step. I know I've said this a couple times, but when we're trying to determine what type of mechanism something goes through at the end of the semester, most things that go E1 will also go SN1 and vice versa. We can differentiate between them a little bit, but often you're going to get both products. So same first step and intermediate. As with SN1, right? Same rate law as with SN1. So next thing that happens, and I'm going to use a neutral nucleophile. And I'm going to have this hydrogen. We need to show it because we need to remove it. And some lone pairs on that hydrogen. I should say a neutral base. So water is going to grab onto that proton. And then I do have a positive charge there, so those electrons are going to go down to create that pi bond. So water took the proton, those electrons go down to create my pi bond, and my product is this alkene. I do have hydronium ions floating around, right? Water after it took that proton, and then Br minus. Again, I'm really just focused on the alkene itself as far as showing me the product. I do want to look at a little bit more about the alkene product. Our product for both elimination mechanisms are going to follow Zaysev's rule. So Zaysev's rule. And Zaysev's rule tells us that the product, our major product, we should say, from our elimination reaction is the more substituted alkene. So the major product, the one that we're going to get most of, so from the elimination, is the more substituted alkene. Remember, we had said previously that the more substituted alkene was the more stable alkene. So if you have an option between making a tertiary alkene and a tri-substituted alkene and a di-substituted alkene, the tri-substituted one is going to be my major product. And by major product, I mean we're going to get some of the other product, just not as much. So for example, if I gave us the following alkyl halide, let's do this one. Sorry, this is messy. And do a base. And it doesn't matter the mechanism so much on this one. I just want to focus on the product. So we have options. I have a proton here. So we can remove that proton and we can remove that halogen. It's the only halogen, so that halogen. And then the double bond would be between those two carbons. So I would have my double bond here. So that's one option. The other option is I do have a hydrogen on this carbon. We could remove that hydrogen and then my halogen. And I would get this alkene. So my first one, this is di-substituted. And then my second one, this is tri-substituted. And we would actually produce both of those. From this reaction, both of those products would be possible. So both possible. But most of it would be the tri-substituted product. So since the tri-substituted product is more stable, and Zaysev's rule says we want to form the more substituted one, the more stable one, this is going to be my major product. And the proportion varies. It could be 80% of it, it could be 70% of it, it's hard to say, but most of the product could be 90%. I'm never going to ask you to give me a percent, but just know that most of it is going to be that tri-substituted. This would be considered a minor product. Unless I specifically say draw all possible products, which I may do, that happens, know that the major product is what I'm looking for. So just kind of a note. Unless told, and this would say in the directions, to draw all possible products, you only need to show the major product. And there are instances where I will ask for all. I want you to be able to recognize that we can get two different products from it. But there will be situations where I just want the major because I want you to know what the major product is. So note, unless told to draw all possible products, you only need to show the major product. And again, our major product is our more substituted product. right? This reaction, elimination, is going to follow Zaysev's rule. The major product is the more substituted